an area of partial negative or an area of partial positive charge anywhere on oil molecules. So if there's no partial charge anywhere in an oil molecule, will it bend toward a charged cone? No. So, is it going?
Yeah, I did.
Yep.
Or like 18 short videos. Oh, Bethany, will you charge up the comb? Thank you. So didn't have enough oil at home for everybody, and oil would be a horrible mess.
A little bit greasy.
Yeah. We'll just do this.
This is brought in the next flaming stream.
Okay, so Bethany will bring the charged comb near this not streaming oil. Hold on. We'll just go back to the other way. Okay. And we see the stream of oil really doing nothing. So nothing happens when you bring the stream of oil near a comb because oil's not polar. It's not affected by the electrons on the comb because there's no area partial negative or partial positive. Thanks, Susanna. Okay, so when you finish this observation in that same step that you wrote this, the charged comb has no effect on the stream of oil. We don't see the stream of oil bend toward the comb or away from the comb. It doesn't change. Now, here is the trickiest question. Even my physics students sometimes miss this one. If the comb could be given a positive charge, it's really easy to charge a comb negatively because we can collect electrons from our hair. Giving something a positive charge is much more challenging. But if we had a comb that was positively charged, and we brought it near the stream of water, would the stream of water bend toward the comb like it did for the negative charge, or away from the comb, or would nothing happen? So think of your answer. Everyone think. Okay, so I'll let Joshua tell us. Just like the other one? Lily, do you agree? No, don't tell us yet. Lily, do you agree?
Because negatives attract electrons, the negatives attract positives, so the positives are going to turn towards the negatives.
So you think it'll...
all the negatives are going to turn towards it. They're going to still bend towards the comb.
Okay, so it doesn't matter if the comb is negatively charged or positively charged, the stream of water will still bend toward the comb. Okay, it bent toward the comb when the comb was negative because its positive end was attracted to the comb. If the comb were positive, it would just be attracted to the comb because its negative end would be attracted to the comb. Exactly the same thing would happen. If you had a positive comb, your results would look identical. You couldn't tell the difference between a positively charged comb and a negatively charged comb just by holding it near a stream of water because the positively charged comb would just attract the negative end of water and the negatively charged comb would attract the positive end of water, and the results would be exactly the same. It would bend toward the comb. So, if the comb could be given a positive charge, the water would bend in the same direction, which you can write on that blank, in the same direction, or you can just circle in the same direction and mark your answer there. But that is a confusing thing. It seems like having the other charge would make your results do something different, but it doesn't. Because of the polar nature of water, it has both a positive end and a negative end. It's attracted both to positive things and to negative things. And so the Y there, the Y, change color, would be the negative end of a water molecule is attracted to the positive charge, or whatever you have the charged. Okay. Now we talk about oil. Oil is a what?
Non-polar molecule.
A nonpolar molecule. So oil is a molecule, or a nonpolar molecule, and it is made up, does anyone know what two elements make up oil? Gasolines, oils.
Air.
Anyone? Have you ever heard, like fuels and oils called hydrocarbons before? Hydrocarbons. Hydrocarbon just means that that molecule, and there are so many, because hydrogen and carbon combine together in many different ways. So oil is a molecule made up of carbon and hydrogen. Carbon, and I just wrote a C for that because that's the chemical symbol for carbon, and hydrogen, hydrogen, which has a chemical symbol of H. So oil is a molecule made up of carbon and hydrogen. Now, neither of these elements takes more than its fair share of electrons from the other. They attract electrons similarly to each other. So, oil is nonpolar. Lily just told us that. Oil is nonpolar because carbon and hydrogen aren't like oxygen where they hog the electrons. They attract pretty equally. Oil is nonpolar. So discuss the behavior of the stream of oil molecules near the charged comb. Jessie, what do you think? What happened when the oil came near the charged comb? Did it? No, nothing happened. So your discussion is simple, nothing. Nothing happened. The oil did not bend toward the comb or away from the comb. It just stayed in its normal stream because it's nonpolar. It's not attracted to a charged object or repelled by it either. So that last blank down there, discuss the behavior of the stream of oil near a charged cone. Nothing happened.
I was just paying attention to the one on the top, on the top of it. Neither of the elements take more than.
Oh, neither of these elements takes more than its fair share of electrons, so oil is nonpolar. A nonpolar molecule has two or more atoms that all share their electrons evenly. No one takes more than its fair share. So if you flip over to the back when you're ready, did I collect all the messy things? Okay. Water is what kind of compound? We review again, Ryan. Polar or nonpolar? Water. Polar. Water is a polar compound, so fill that in. So there are areas of partial positive and partial negative charge on a water molecule. Right here. And Patrick, oil is what kind of compound? Nonpolar compound. Electrons are shared evenly throughout oil molecules. I have a note here, show periodic table. So if you look in the probably front or back cover of your textbook, where I just pulled up, I didn't bring my big one because we used it in chemistry, and it is still down the hall. I don't have one. Awesome. Here. Okay, here I have a copy of my periodic table. Your books also have a periodic table in them. And on back to school night, I think I passed out a copy of the periodic table that you may use on tests. Probably. I hope. Okay. So, salts like table salt, and there are many other salts than the kind that you put on your food. Like we call that salt, but there are a lot of kind of salts. Salts are made of a what and one or more what. Does anyone know that? That's a hard one. Maybe you had it in your reading this week. So, all of these green elements here are metals, and all the red ones are nonmetals on your periodic table in your book. Now, some periodic tables look a little different. And these white and brown guys are also metals. So green guys are metals, red guys are nonmetals, and salts are made up of one green guy, which is a metal. And these guys can also make up salts too, but I think they keep it simple for you guys and give you the simple standard metals. So salts are made up of one metal, that first blank, and one or more non-metals. There we go. And salts are called ionic compounds. So salts are made of a metal and one or more non-metals, and these are called ionic compounds. Ionic compounds have one metal and one or more non-metals in them. Like table salt, the kind of salt that you put on your food has sodium, which is a metal, and chlorine, which is a non-metal, and it's called sodium chloride. There are many other types of salt. Ionic compounds are not held together by, so what holds the water?
Chemical bonds.
Right, not held together by chemical bonds. So if we have a water molecule like this, we talked about how these sticks represent chemical bonds, but ionic compounds aren't held together by chemical bonds. They aren't held together by the sharing of electrons like that. The nonmetals in ionic compounds completely steal electrons from the metals. Okay? The nonmetals steal the electrons completely from the the metals. So this means, like if we take table salt, for example, NaCl, a sodium, which is a metal, and a chlorine, which is a non-metal. So when we form this not exactly a chemical bond between these ionic compounds, we call them ionic bonds. What really happens is the chlorine, the non-metal, steals the electron and takes on a completely negative charge because it has one whole extra electron than it should. And the sodium got that electron stolen from it. It lost a negative electron, so now it has a positive charge. So the chlorine gets one extra negative electron, the sodium loses one. So the sodium gets a whole positive charge and the chlorine gets a whole negative charge, which is different than the partial negative and partial positive that water molecules get. But they stay bonded together. Why? What kind of attraction do we know exists between something with a positive charge and something with a negative charge? Yeah, they attract toward each other. They don't repel each other. They attract each other. So ionic bonds are really just the positive charge attracting the negative charge and vice versa. Ionic compounds are held together by, I'll call that electrostatic charge. We talked about static electricity, the attraction between those two charges. Max?
So what would an ionic bond actually look like? Would it look just like a chemical bond if we were to draw out an atom of?
Nobody draws ionic bonds. If you did draw one at this point, that would be okay. But really, it's not a bond. It's not a sharing of electrons. It's an electrostatic attraction. It's an attraction just like the comb is attracted to the stream of water, because positive charges and negative charges attract things together, hold them together. So it's like a force caused by static electricity, basically. But they're not. That's not a chemical bond. So this means the nonmetal, which is chlorine, develops a negative charge, and the metal gets a positive charge because the nonmetal gains an electron, which is negative, so it's negative. And the metal loses that electron, so it becomes positive. Ionic compounds bond together because of the attraction between positive and negative charges. So we're kind of a third of the way down the page now. The nonmetal gets a negative charge, and the metal gets a positive charge. Then they attract each other because of their charges. So now we're going to talk about how ionic and polar